to the internal keyboard controller and then sent to the processor via these 4 pins. But how this data transfer taking place? There are two fixed specific port. One is 60H, another is 64H, right? 60H and 64H, that is our CPU. Our CPU can communicate with the keyboard controller present inside a desktop keyboard. We can communicate directly, the processor can directly communicate with the controller present inside the desktop keyboard by the address 60H. That is, if we want to read the information from the 8048 microcontroller present inside the desktop keyboard, the CPU has to use the address 60H, right? Similarly, if the processor has to read the information 8042 keyboard controller present inside this IO controller, then it has to use the address 64H. We will not go into that detail, but why I have used is because some people want to play with it, so you can use this information in playing, right? And this is the way the data is transmitted. And in case of laptop keyboard, both keyboard encoder and keyboard controller is present inside this IO controller. So the keyboard pressing is first processed by the keyboard encoder, and the data is then transferred to the 64H address of keyboard controller, and then it is sent via these 4 pins of LPC bus, right? And but this serial IRQ pin is important. Serial IRQ denotes whether the data is coming from a touchpad or from keyboard, right? So in the next class we'll see the other parts of this IO controller, because this is a big section. IO controller is in fact like a mini laptop. It is having everything inside it: RAM, BIOS, microcontroller, everything. So we have to discuss these things in great details. So my next class would be tomorrow, and I'll give you the next video tomorrow of the other parts, and I promise that I will finish this class as fast as I can, but I must cover all these things, so it's taking a little bit of time. So goodbye to all of you, and hope you enjoy my classes. Thank you.
Good morning everybody, and in this class I'm going to cover the BIOS dissection and deassembly process. In my previous class I had covered one part of the IO controller, but I have chosen this topic to explain it because this is one of the major problems faced by the technicians while repairing the current type of board, where we have two kind of ICs, BIOS ICs, EC BIOS and system BIOS. But when you try to find the BIOS backup on the official website, you get an exe update, and you may try to unzip this exe update by 7-zip, but when extracted with software like 7-zip, you find a .fd files or some files, but the size of that fd file is sometimes larger than the actual required size, or sometimes smaller than the actual required size, or when you require both EC and system BIOS separately, there is a together the both are combined file. So we need to devise certain approach, certain techniques to deassemble that file and get our required size. So in this class I'm going to discuss the approach and techniques, and please note the approach and the techniques will vary with model and model wise, right? So here we will discuss some 3 to 4 dissection and deassembly, and after going through this 3 and 4, 3 kind of dissection and de-assembly, you'll have a fair idea of how to dissect it, how to deassemble it with the other models. Okay, so this is one of a very important class, and you may have to rewind this class many times to understand it, because certain things may not be clear when you go through the first videos playing, right? But when you rewind it, you'll get it everything. And now the classes will be more faster, and I'm trying to finish this class in around 15 days. So let's start with the today's class of BIOS dissection and de-assembly process. To start with this class, we'll need some more softwares, and let's see what are the required softwares. Okay, so we would require some kind of software for this dissection and de-assembly process, and one of the very important software for it is Ultra Edit. Okay, so let's open this Ultra Edit. You can download this Ultra Edit by searching Ultra Edit in Google, or I can give you a backup of the software Ultra Edit. This is basically a hex editor, and we'll go through what is actually a hex editor is. Let us open this. So this is Ultra Edit 32, and this is a very fine hex editor. And this hex editor, you'll find many things for edit, because basically we have to go through these functions of this editor, and the functions are, let us first convert it into hex. Okay, let's go and open it into the, right now we have to just open one file. So let's open one file to show you. Okay, this is my folder, and in this folder I have put everything Ultra 32. So let's open this. We'll go here and open this file. Yes, but you see this is looking very tedious. You cannot see anything. So here there is one function in edit, and you type hex edit. Now this file is looking very good, right? And to explain hex, let's first go through what exactly is an hexadecimal format, right? So let's check here. This is a hexadecimal number system. Well, to simplify things, let me explain first what is the difference between a binary number system and hexadecimal number system. See, our processor, the processor in a notebook motherboard, or processor in a desktop motherboard, or processor in a mobile, they don't have much brain, you know. These are man-made, so they don't have much brain, so they cannot decipher very complex sentence. The processor are based on very simple approach, true and false. They will check any scenario with condition whether it is true or whether it is false. So if true, they will do this action. If false, they will do this action. So true and false, only two states a processor works in, that is 1 and 0. So in computer hardware, on digital computer architecture, we use binary number system to represent data, right? And as you know, 8 bits is 1 byte, whereas in hexadecimal number system we use hexadecimal number system to represent that data, because in hexadecimal, when we use hexadecimal number system, then the entire data is compressed. We can represent that same data in less space, right? Because you see, the hexadecimal number system is similar to decimal number system. The decimal number system is 0 to 9, 0, 1, 2, 3, 4, 5, 6, 8, 9, 10 digits, 10 numbers. But in hexadecimal numbers, it is same, but you see, it is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After 9, this is 10, 11, 12, 13, 14, 15. But in here the decimal number system ends, but in hexadecimal number system we go till A, B, C, D, E, F. So we find we can represent the same data in binary with hex in less space. So we use hexadecimal number system to represent data. Alright, you got my point? Now there is a very easy way to convert a binary number into a hexadecimal number. Let's see. As you know, a byte is 8 bits, so let us consider 8 bits. Okay, 0 0 0. This is how much? 1 2 3 4 5 6 7 8, right? This is 7 8. This is 1 bit. Now we have to convert this into hexadecimal number system. So how do you convert? See, we choose right from the right side. 1 2 3 4. This is 4, right? So put a space. Now you convert this into decimal number system, right? You can convert into decimal number system. You know how to convert this? Let us convert 0 0 0 into decimal number system. This is binary, right? This is binary, so we have to convert it into decimal. So how would we convert? You know, 0 wait, 0, this will be all 0 in decimal. And how would we convert this into decimal? 0 1 2 3, that is 1 into 8, 1 into 8 plus 0 plus 0 plus 0, right? So this will be 8, right? 8. So we can write in hexadecimal as 80. You got my point? We have to convert this 4 bits into decimal, and we have to convert this 4 bits into decimal, and we can write here, and this is hex format. The entire binary format has been converted into hex format in only 2 characters. You got? So this is why we use hexadecimal to represent data, but in actual format binary system is used by processor, because processor works on logic of true and false. Also this binary number system is used to prevent the data loss or data corruption, because suppose if one byte is moving from this chip to another chip, what maximum can be done? 0 can get converted into 1, or 1 can get converted into 0. But we can check whether this error has caused with help of parity. I won't go into much detail what exactly is parity bit, but you can search in Google why parity bit is required and how it helps in letting us know that the data has been corrupted. Here the main significant point is we convert the binary form into hexadecimal form to analyze the data. Okay, so let's go back to the ultra edit software. In ultra edit software, you'll find, we'll go click edit, you will find many options over here. For us, the important options is hex, insert and delete. You'll find here options insert and delete. So if you put your cursor over here and you want to delete data up to here, right, then what you have to do, you have to edit, hex, insert, delete, and then you have to enter data, and it will delete the values after the mouse, right? The data after the mouse will get deleted, whatever values you put over here, and rest data would shift here, right? So we'll use this software to dissect and deassemble the BIOS. And for me, I have many important case study over here, but we'll cover the case study like Dell 5520, V3450, 6930P, E325. This 4 case study will cover in the today's class, and the rest we'll cover after the finishing of IO controller, maybe if we get time. So by this 4 dissection and deassembly process, you will have a fair idea of how to do it. Okay, so let's open our PowerPoint presentation, and this is E325, IBM E325, and in IBM E325 we have 2 kind of BIOS chip. One is the system BIOS, and another we have EC BIOS. The system BIOS is W25Q16. Q16, that means it will have 2 MB of file. All right, you divide it by 8 in the W like format. You divide it by 8, you'll have 2 MB of file. It will have a 2 MB of file. Required file is 2 MB, while it has an EC BIOS MX25L512, and it will require a 512 KB of EC data. All right, so let's see the IBM E325. There is another way to extract the IBM files, but that is only valid for the older version of IBM. Since when IBM was overtaken by Lenovo, the Lenovo has used its own way to pack these two BIOS file, and they now pack it in little complex way. Earlier the IBM was packing the BIOS in a very simpler way, and we can extract this data with one command like ex file. We could have extracted this file with ex file, but now the extraction is a little bit more difficult. So we'll take the case of IBM E325, that is IBM Lenovo E325, and we go to my folder, and my folder is here, IBM E325. When we download the BIOS update from the website, we get a file like 8nuj13us. Let's delete it so that you could be understanding this. All right, let's close it again. Be very specific and precise. We get this file 8nuj13us. Now this file is 5 MB, right? 5 MB, and our and you see in the our presentation we have 2.512. the total, if we add it, 2 MB and 512 KB, it's around 2.5, less than 2.5, right? So there must be this file. If we extract this file, we might get, so we get an idea that yes, this exe update file would have these two files together, because this file size is greater. You see, 5.029 MB, whereas our required is around 2.5 MB. So that means we have to extract this to get these two files. All right, so extracting is very easy. You just double click it. All right, double click it. Next, we'll go next, no problem. We'll follow all these steps. Here you can change the extraction, because we'll not go into the C driver. Let us browse this and we change it to our location, and our location is desktop. So I'll go to the users and use this one, and we go to desktop, and this is my folder, and we go to IBM 325. Okay, we go to next, install, and you see my folder is extracted. Let us check out and finish. So this is our folder. We double click the folder and we find two files, right? There are no such related files over here. So you find the 8NET37WW and there is 8SET34WW. What does these two files represent? This 8NET37WW is for Lenovo E320. There are two models coming in IBM Lenovo, E320 and E325, and this is 8SET Lenovo E325. So we double click it and this is our file. This is our file, right? So we will copy this, all right, and we will put over here, all right, and now we'll open this with hex editor, with our favorite hex editor. I'll try it. We'll open it with I'll try it. Double click it and let's open this file. And our file is saved here in E325. This is our file. We open it, right? Let us rearrange it in hex editor. Yes. Now my file is hex rearranged. So what we have to do is, we know in a very interesting point that I will tell is, you have to note this thing is, in this kind of file, first BIOS is there and after that EC is there. That is, first the BIOS file is there and after that EC file is there. In every kind of exe update, when you extract exe update and you get such kind of file, .fl1, please kindly note, in IBM Lenovo, .fl1, this format, .fl1, this is the main file that we have to work on, not any other file. This is the main file that we have to work on, .fl1. And note, you'll find many kind of extension like .fl1, .fd. In any kind of this files, first the system BIOS is there and after that EC BIOS is there. So what we require is, we require the 2 MB file, right? We require the 2 MB file. So we'll go in the Ultra Edit and we'll go till 2 MB. Let's go, where is our 2 MB? We have to 2 MB would be where this is 2, it will come 2 over here, right? So let's go to 2 MB. Wait, 2 MB. Move downwards. Yes, we are reaching to our 2 MB. That is the system BIOS. We are reaching. Yes, wait. Yes, this is, we have to go ahead. 2 MB, right? And this way you have to, this is the approach of dissecting the BIOS. Here you have to be very cautious, because anything that you delete would make this BIOS corrupt and it will simply destroy your system. So you have to be very cautious when doing this, and it will require some practice, and you can try practicing it on your computer. Let's find our 2 MB file. Yes. So here, data from the starting to here is 2 MB, right? Data from starting to here is 2 MB. So rest data we have to delete, right? Because this is useless. Our system BIOS is only 2 MB. So what we'll do is, we'll put the cursor over here. We'll put edit, hex insert delete, select delete, and you put as much values to delete. You can put something like this, 189.345.6. all right, and you got this file. Everything is deleted. You see, everything is deleted up to here. Now this file, you can save this file as, E325 system BIOS, that is smbios.rom, and you see it in your folder of IBM 325. You see this is 2048 KB, that is 2 MB. How is this is 2 MB? You see in the calculator. Let's use the calculator, and wait, my system is a little slow, and we'll use calculator to explain each and everything. This is calculator 2 MB. In 1 MB, you know, 1024 KB. So 2 into 1024 KB, that is 2048 KB, right? And 1 KB is 1024 bytes. So we multiply by, sorry, this is byte, 2048 KB. You see, this is 2048 KB. So our system BIOS is 2048 KB, that is 2 MB. So we got our system BIOS. Now the question is to remove the EC BIOS, right? Now the question is to remove our EC BIOS. So we'll remove the EC BIOS. Now we'll remove our EC BIOS, right? In here, in our Ultra Edit, we'll go back, we'll open our earlier file, all right? This set, this file, we'll edit, we'll go to the hex edit. This is our original file, right? This is our original file. Now what we have to do is to remove our 2 MB system BIOS. So the remaining would be EC BIOS, right? Remaining would be EC BIOS. Let's go and find the calculator. 2 MB is how much? 1024 KB, right? And if we multiply by 1024, we'll get that much byte, right? So this is our byte. 2 MB is 2097152 bytes. So if we delete from here 2097152 byte, will get our EC BIOS. So what you have to do is very simple. Edit, hex insert, delete, put the values 2097152. Alright, this is the value, and you put OK. Now this, you save it. You've already deleted, okay, and you save this file here in E325, and this is your EC BIOS .rom, and you open this folder, EC BIOS.rom. Well, this file is little less than 512 KB, but a very important analysis if you do with the EC embedded controller is that they read the data sequentially, so the size is not important for the EC BIOS. As of now, the size is not important for the EC BIOS, but the system BIOS size is really important. So this is EC BIOS.rom. This is the actual EC BIOS.rom, and you can run this file in the EC BIOS and it will work perfectly. So this is the BIOS dissection and deassembly for the Lenovo E325. Kindly note, we require the .fl1 file to deassemble and dissect it, and I would try to give credit to one of my friend for this help, because I was trying to dissect and deassemble a different file and I could not find anything in that. And thanks to Mr. Lee, he is living in Shandong province of China, and a great credit to him for helping me out this, and thank you to him, and in Chinese I can say "谢谢" to him. So let's go back and see our another BIOS dissection file. In this thing, I think you are very much clear. You have to rewind this. We have extracted this because this is 5.029 KB, whereas we require 2 MB and 512 KB together. They are less than this update file. We have extracted this file. We have found two folders. This is E320 and this is E325. Here we are considering about E325. So we have opened this. We have copied this over here, and we have opened it with Ultra Edit. And as I told, in this kind of file, the system BIOS is first, and after that EC BIOS is there. So I have selected first the 2 MB file. I have gone to 002 up to there. I have selected that data, deleted the rest. That is our system BIOS. We again reopened this file and we deleted the 2 MB. 2 MB is 201024 KB is equal to 201024 into 1024 bytes. We have deleted that bytes. Rest file is EC file. This is very simple. So I have started this with a simple procedure. In the next BIOS dissection, that would be little tedious. Okay, so we have another, let's see another file for BIOS dissection, and we have an interesting case study of Lenovo Dell 5520, Dell Inspiron 5520, also called as Dell Inspiron 15R, and this is a very common model. And in Dell Inspiron N5520 we have two kind of BIOS chip. One is system BIOS, that is W25Q32, that means it will have 4 MB of file, and EC BIOS, this is MX25L160E, that is it will have 2 MB of file. But if you download the BIOS update from the website, you will find it as 4.34345 KB. That means this update is compressed. These two files are compressed together in one update file. So we need to first extract this compressed file. We double click it, yes, and we'll go to see it in the temp folder. Do not click OK. If you click OK, the extracted file will go away. So we'll go to the C drive, we'll open the users, okay, users, we open the users, we go here and you see there is a hidden folder, app data. Inside it we go to local, and in local we have to go into the temp folder. In the temp folder you see there is extracted 7Z S9C3G. You double click it and there would be .fd file, and this is our .fd file. So this is the important one. We copy it and we'll paste it over here in our folder del 5520 and you paste it. This is our file, okay, this is our file.
Okay, so now we have extracted the .fd file from the BIOS update that is present on the official Dell website. So you can see this file is 6.26272 KB, right? And our file needed is approximately same, that is 42 plus 6. So we can notice that this is the file we are looking for, and we will extract the system BIOS and the EC BIOS from this file. So let us open our software Ultra Edit. Okay, we'll open the Ultra Edit to extract that file. Alright, this is a very good hex editor. We will open this file .fd. Yes, but please note there's an interesting point over here. In .fd file, usually in Dell, the first 128 KB is header file. So we have to delete the 128 KB, that is header file, right? You can see in the calculator, wait, in the calculator, we can see 128 KB is 1024 bytes, that is 131072. So we'll place the mouse over here, starting point, and we'll press edit, then we go to hex insert delete, we'll choose delete over here and we'll put the number 131072. so we'll delete the 131072, very cautious here, and we have deleted it. Now we can save this file as biosback.rom, and this is our file. From this file we have to extract the 4 MB. As spoken, the first 4 MB is system BIOS, so we'll select the first 4 MB and delete the remaining to get our system BIOS. 4 MB is 00, you see 00H2 003 3FF. You can see over here, you can see over here. We'll select the first, okay, E F F F F F. Yes, we'll go down, we'll go down. All right, F3FF. The first 4 MB is system BIOS, so we will select the first 4 MB, delete the remaining and save it as a systembios.rom. okay, systembios.rom. so we have to follow very smoothly, no error. Yes, we'll put our cursor over here, right, and the data above this address is system BIOS, so we'll delete the remaining data. You go over here, hex insert delete, put values as much as it deletes the value, right? Still not deleted remaining, so we'll select again, we'll find 1356 unit 9. Alright, so all the data is deleted after that. Okay, so this is our system BIOS. You can save it as systembios.rom. okay, and you see in the file, go here, Dell 5520, and you can see this is systembios.rom. okay, 4 MB file, 4 into 1024, that is 4096 KB. You see, this is exact system BIOS.ROM. Now what we'll do is we have to extract the EC file, right? We have to extract the EC file. So we'll open again our Ultra Edit, alright, and we'll open again that our file.fd, yes, alright, and we'll delete the 4 MB data. So what we'll do is 4 MB of data is how much byte? You use calculator. 4 MB is 4 into 1024 KB, right? Multiplied by 1024, that will give you bytes. So 419434, you delete 41, starting 419. As I have said, the first 4 MB is system BIOS, the rest is EC BIOS, right? Rest is EC BIOS. So we are deleting 419404. You delete over here and you can save it as now as EC BIOS, EC BIOS.ROM, and you can see EC BIOS is 2176 KB, right? 2176 KB, 2 into 1024 is 2048. So this is little bit more. This 2176 KB is little bit more, but I said the EC BIOS is done sequentially, right? Is done sequentially. So some BIOS programmer will handle this file with no problem, but some of the BIOS programmer will throw error. So what we will do is after 3FFH we'll delete the values, right? You see, some BIOS will give you no error. So this is EC BIOS, right? So we got EC BIOS and system BIOS. Well, some programmer may sometime give you error, but not with this Dell 5520. I've never observed with this, but if they give you some error, then you have to delete the file after 2048 KB, right? So this is the way we have got EC BIOS and system BIOS. And we will take another case of, let's go back to our PowerPoint presentation. What is our next case? And our next case is 6930P. So we'll follow the 6930P case. Okay. So now let us see the HP 6930P. This is also very interesting kind of case study with us, because there is little differences from the earlier two dissection that we have done, the earlier two dissection separation we have done. This 6930P is having one system BIOS chip, that is SOP8W25Q32 SPI 32. That is, this is 4 MB BIOS, 4 MB BIOS chip, right? So what we will do is, let's this is an EFI BIOS. So in case of EFI BIOS, always remember you have to take backup from the chip, from the BIOS chip of the notebook motherboard. So here, and how you can take backup, the best way to take backup is to use programmer. So by using programmer, we'll save the original BIOS as biosback.rom. You got it? This is an EFI BIOS. So in case of EFI BIOS, we have to basically use little content of the original BIOS file. So what we'll do is we'll take the, you see here we have written, we need to first back up the original BIOS file present in chip and save it as biosback.rom. Okay, now we download the exe update file. If you will extract it, and by extracting it you will find two files, that is SP 45530d.exe, sp45530u.exe. D is for discrete, U is for integrated. Discrete means separate graphic chip, integrated means all integrated. So here we are dealing right now with discrete. So you double click this .exe and a rom.rar file will appear, and we know very well we can extract this rom.rar file with winrar. So extract it with winrar, you will get rom.bin, but the size of this rom.bin file is very less. It is very less as compared to the requirement of 4 MB. So what we will do is we'll open this rom.bin with our ultra edit. You see, we'll open this with ultra edit. Let us open any file for just sake purpose, because I don't have right now the, we'll just open this one right now, the backup, the original backup of 6930p. So we have opened it. Let's close the earlier thing. Okay, so we have opened this and we'll copy all this. Let us consider this to be rom.bin. So if this is rom.bin, we'll copy all the data. We'll copy all the data. Okay, and now what we'll do is we'll open the BIOS back.rom. What is BIOS back.rom? We have copied the original BIOS file from the chip using processor. We'll open this BIOS back.rom. We'll pull the cursor to 254x0h address and we'll paste the data of rom.bin. We'll paste all the data from the rom.bin, and you can see the cursor will be at this address, and you have to delete the remaining and save it, and this is our original system BIOS file. So you see, we are using the back.rom file. You know, rom.bin, what we have extracted rom.bin file, it is very less in size as compared to our requirement of 4 MB BIOS. That means we have to use the original backup to add it and make our system BIOS chip. So what we'll do it, we'll open this rom.bin, we'll copy all the data, we'll again open this BIOS back.rom, we'll go to 2508 address, we'll paste it, and we'll delete all the data after 400H, because we require data up to here. This is our 4 MB. This is our 4 MB data. All right. This is our 4 MB data. So, and we will delete all the remaining data and we'll save. And this is our system BIOS file. Now we'll consider, this is one example of how to handle an EFI BIOS. In the next case study, I'm going to handle the Dell Vostro 3450 BIOS, and there we can see a little more complex when we have an EC BIOS also. So let's go to our next case study and check Dell Vostro 3450. All right. So now let us consider the case, our next case, that is Dell Vostro 3450. This is, see, I have tried to move sequentially using all the concepts. First I have tried with a very easy IBM 325, then I have moved to Dell 5520, then I have moved to 6930p, a little EFI, right, that was EFI, and now I have come to Dell Vostro 3450. This is an EFI system BIOS plus EC BIOS, right, plus EC BIOS. So what we'll do is, let us consider this Dell Vostro 3450. In Dell Vostro 3450, you have two kind of chip. One is the system BIOS, that is MX25L3205. This is system BIOS. 32, that means 4 MB file. EC chip is W25Q40, that is 512 KB EC BIOS. Now what you will do is, when you download this file, when you download the BIOS update file from the website, and you see in the property this is 9.63 MB, quite horrible. We require just 5 MB and this is 9.63 MB. So that means we have to extract we have to extract BIOS from this. We have to extract BIOS from this. All right. So let's check our folder. We'll go to the I'll go to my desktop and open my folder, and BIOS dissection and deassembly. We'll go to 3450. Here is, let's close all this. Okay, here is our exe file. You can see in the properties. All right, you can see in the properties 9.63 MB, quite horrible. We require just 4 plus 4, close to 5 MB, right? We just require close to 5 MB. You see, wait, 512 KB, right? Less than 5 MB, but the exe update is 9.63. all right, 9.60. so what we have to do is we have to extract this. So let us put double click, okay, and let the system respond. Yes, it has extracted. You see, it has extracted, and we will get this file bios1.wph from here, and we'll copy it and we'll put it back in our folder, that is BIOS dissection and deassembly. Put it over here. Now this is close to our requirement. So what we'll do is we'll open this with Ultra Edit. Wait, let us close this. All step by step, you can try yourself. Sorry, this will open, and this is our dissection. Vostro 3450 will open this. All right, and what we'll do is we will delete the datas from 00. Wait, we'll delete the data. Just follow over here, and we'll delete the data from 00A0H. We'll delete the data from here to here. You see, we'll delete the data in this from here to here. We'll just delete this data. Select and delete this data from here. A0H. All right, 00A0H. 00A0H. You see over here, A0H. So we'll delete this data. That is the surplus data, because what our requirement is 4 MB and 512 KB. So we'll just cut out. Now our cursor is over here. We can save this. Just save this. All right. Now this is system BIOS plus EC BIOS. So what are the steps? We will have to just move our cursor to 3FF over here. 3FF 4 MB. The first 4 MB is system BIOS, rest is EC BIOS. But then again there is a little twist. So let us first just extract the EC BIOS, then we'll talk of the system BIOS, because this is EFI, so we have to do something with our BIOS backup of the chip. All right, let us first do our step. We have to extract the first 4 MB for the system BIOS, rest is for the EC BIOS. So we'll go to here, 3FF. all right, closely we have to just follow closely, no missing. If you delete anything, you're yes. So what we have to do is we have to delete the data after this. Then the top 4 MB is our system BIOS. The top 4 MB is our system BIOS. So what we'll do is we'll just go here, we'll do insert, delete, and we'll put value, any value that can delete data is up to here. You see all the values deleted, and we can save it as we can save it as system bios.rom. alright, we have saved this as system bios.rom. alright, let's close this and let's open again our WPH. alright, let's go to hex edit, hex edit. alright, and now what we'll do is we'll just delete the 4 MB and the remaining would be our EC BIOS. Same procedure like we have done it, right? Same procedure like we have done it. We'll just, this is all procedure we have done till now, and BIOS.ROM. Now we'll delete 4 MB. 4 MB is how much? Let us use our calculator. 4 MB is how much? 4 into 1024 KB into 1024 bytes, that is 4194304. so what we'll do is we'll just delete, we'll put the cursor over here on the top, we'll delete, hex insert delete, choose this, and 419, where is our calculator? 4194304, and just put it. Now this is our EC BIOS, but our EC BIOS has to be 512 KB. So what we can do is after this value we'll get the real EC file. Some BIOS programmer can program this EC BIOS. Let us save it as, let us first save it as EC BIOS. Some BIOS program can program, but this file, you can see this file is more than this, right? More than 512 KB. So what we'll do is we'll delete the data after 8, that is 512. 8, we'll delete the data after 8. You see here, let's go to 8. Triple times 0, 8. Yes, we are reaching. Here we'll delete the data from down, then we'll get our 512 KB. So what we'll do is again we'll go here and we'll put values 3, 4, 5, 6, 7, and here is our data. Now this is our real EC BIOS. Save, right? This is our real EC BIOS. Save that. Okay, wait, EC BIOS, save as, yes. Now we close it. You see our EC BIOS is 512 KB. Finished. We have got our EC BIOS 512 KB. Now this EC BIOS has nothing to do with the EFI. So now the question is, we have got our system BIOS, but this is not EFI compatible. So we'll follow again the procedure over here in our PowerPoint presentation. Till now we have got our EC BIOS. All right, we have got our EC BIOS. Now what we'll do is, it is also, you see, for V34504 EFI BIOS file, it is necessary to read out the original BIOS chip data file, right? We have to read out the original chip data. Now what we'll do is we'll just open our saved 4 MB file. We'll just save our 4 MB file. We have to open again our Ultra Edit, and we have to open again our Ultra Edit. All right, and we'll open our system bios.rom that we have saved from this. Okay, system bios.rom, we go to hex edit, yes, and now what we'll do is say the mouse is Now we will delete this much byte 1572864. What is this? 1572864 is 1024, right? This one is KB 115. So we'll delete this data 1572864 byte from this 1572864 byte from this hex. Delete 1572864. This I have basically doing cross back, but I am writing it over here. You can see actually I have to make 4 MB, so I am adding this, deleting 1572864. We delete this data and we got this. Okay, we got this. Now what we'll do is you follow the next procedure. Select all. We have to copy all. All right, we have to copy all, select all. We have selected all, and now what is our next step? Our next step is to open the original BIOS, the original BIOS backup that we have taken. We have to take this original BIOS backup from the programmer. We go to the address, this one, and we have to paste all the data which we have copied till here, we have to paste this data. Okay, and then we have to delete all the data after 3FF, that is the 4 MB. This will give us EFI system BIOS. All right, this will give us the EFI system BIOS. So what we have done here is, first let's start from the very first. Let us start from the very first of E3450. We have noticed that in Dell Vostro 3450 we have two chips. One is the BIOS chip of 4 MB and the EC chip of 512 KB. The BIOS chip here is an EFI BIOS chip. So as seen in the previous case of 6930P, we have to do something with the original BIOS. We have to take backup of the original BIOS, and you can take backup of this original BIOS through programmer. Now we have downloaded the BIOS update, and you can see the BIOS update that we have downloaded is close to 9.63 MB. That means we have to extract this. So after extracting this, we got BIOS 1.wph, which is close to our file. So we'll open this, and we have deleted the initial A0H, and this is 5 MB file, close to 5 MB file. So that is what we are requiring, 4 MB plus 512 KB. Now we have got this file. We'll select the data as done in our previous case. We'll select the data from 00H to 003FFH, right? We'll select this data from 00 to 3FFH, delete the remaining, and save it as BIOS system bios.rom. Okay, now we'll again open this wp1 the BIOS wp1, right? And we will delete 4 MB, initial 4 MB. As I have said, in this kind of file we have first system BIOS, then EC BIOS. So we will delete this 4194304. How this number has come? 4 MB, 4 into 1024 KB into 1024 bytes, that is 419430 bytes. So we have to delete it, and we have got the EC, but EC should be 512 KB. So what we'll select, we'll delete the data after this 800H, and we'll get the 512 KB of EC BIOS. Now what we have to do is we have to change this system bios.rom, right? Because we have to make it as EFI compatible. So what we will do is we'll open the system bios.rom. All right, we'll delete this much of data, 1572864 byte. We'll select the remaining. All right, and we'll open the original BIOS chip. We go to over here 18000H, paste it. Our cursor will go down over here. We'll delete the remaining, and this will be our 4 MB system BIOS chip. All right, so I think I'm pretty much clear, and I will cover the assembly and dissection of around 5 more models, and in that models we have 4010 is one of the model. We have 1535, 1435, We have Lenovo, some more Lenovo models and Acer models, but right now I'll just cover another topic, that is the HP DMI utility. There has been a lot of confusion regarding this tool, when to use this tool and how to use this tool. So let us go to HP DMI utility. This is a very good utility provided by HP. Sometimes what happens is when you flash BIOS of HP laptops, or when you change motherboard of suppose you change motherboard in HP laptop, then some error would occur, like OS cannot be installed, So in that case, what we do is we have to restore the asset, that is through HP DMI utility. And where you can download this HP DMI utility, we have backup of this HP DMI utility. It's there with me, and I can share with all of you. HP DMI tool. This is HP DMI tool, but this HP DMI utility will only run in DOS mode. So what you have to do is you have to take a pen drive, make it DOS bootable, copy this HP DMI utility into that, because it cannot run directly into your Windows. This utility you cannot run into your Windows. You have to run it into DOS mode. Before going into that, let's check what important thing is there. Yes, and you see this kind of tag we have. This is model number, right? This is model number, this is the part number, this is the serial number. All right, this is the serial number, and you may find something like this where the serial number is at the top and this is the product number, or you may have something like this where this is serial number and this is product number. So these are the three kind of tags present in the HP. Let's go to the next slide. As I said, you cannot enter, you can download this HP DMI or NBDMI Fit, that this tool is called, from our website chiptronics.com. But before running this, you have to make a USB bootable pen drive. You have to copy this, and then you can run your laptop into DOS mode, right? To boot from the USB, and then you can type at the command prompt NBDMI Fit, and when you type this interface will be there, 013457, like this. 0 is for serial number, 1 is for notebook model. Let's go to the next slide. 0 means display and set host serial number, the host serial number. 1 will display the machine model, as we have seen. Let's go to the next slide, previous slide. You see this is serial number, this is model number. Okay, so you see 3 is display and set UUID model, 4 is for display and set SKU model code, 5 is for display and set in CTO region code. This is for region code, like whether this laptop is in China, this laptop is in India, this laptop is in South Korea, this laptop is in UK. There are separate region code, and you can find in Google, and you can put the CTO region code over here. If a laptop is for India, you have to put the region code for the India. All right, and this is for display and set PCID, product configuration code, and like this. Let's go to the next slide. We press 0 and we have to put the serial number over here. Serial number you can get at the tag which I have shown in the previous slide, right? You have to put serial number and you have to put 10. In some cases the string length varies, like in some models you see earlier, in some model this is 10 and this is also 10. Maybe in some model this may be less, something like 6 or 7. Then you have to change the string length over here. You have to change the string length over here. Alright, so next, go to the next level. We then press 1 to enter the model. What is exact model? Here, if this is compact processor CQ35, put compact processor CQ35. With the motherboard is of CQ40, you put CQ40, or DV6, you put DV6. Alright, then we press enter, and you have to write the UUID, and below that there will be one option, press 1 to generate automatically. So you just press 1 and it will generate automatically. Press 4 to enter display and set SKU model code. So you can just put the SKU model code. Similarly, CTO and remaining also you can find like PCID, product configuration code. This is very important, and you can find it on your close to your RAM slot in the motherboard, this PCID, right? Or you can, if you don't find, then you have to just put a string of around 17, right? 17 characters. Just put any string of 17 character over here. All right, so we have finished up with the today's class, and in the next class I will cover with the remaining part of the IO controller. We'll finish it up. We'll go to the PCH, then CPU, the complete process we cover, the CPU voltage regulator will cover, all the things we cover, and then we move back from CPU to PCH to IO. That is the BIOS booting process. That is very important, and we'll follow with oscilloscope, and my target is to complete this course in another 15 days. Thank you, and if you have any problems or questions, you can always email me. Please rewind these videos 3-4 times and you'll get an idea. This is just an approach, no methods. There is no methods to disseminate and dissect BIOS file. That is an approach. For each kind of model you may have to do something much different, but the approach is same. The approach is same, the technique is same. Thank you everybody. And welcome to the today's class. In this class I'm going to cover the flashing of embedded flash that is present inside the IO controller. In the previous class I have shown you how to dissect and deassemble the 6 MB BIOS file into 4 MB and 2 MB and vice versa. And before that class I was covering the part of IO controller. I have not yet completed the IO controller class, but in the previous class I discussed about the new kind of IO controller that are coming in the market, which is having embedded flash inside it. And this is most commonly found in boards which have integrated CPU, where the CPU is integrated. Like I have Dell Inspiron 3521 board, where you can see the CPU is integrated, and I have the IO controller KB9012QF, which is KB9012QF, and this IO has embedded flash. And you can see on this board you'll find two kind of BIOS chip. Both are connected with PCH, and the EC BIOS is inside the IO controller. So that's why whenever we require to desolder or to resolder a new kind of IO controller, we need to flash the embedded controller. And for this we would require some kind of special BIOS programmer, and with me is having RT809F. This is the only BIOS copier present in today's world which can program this IO. Only kind of commonly used BIOS copier. So this RT809F, it comes with this copier and this ISP module, okay, and with some CDs. So I'll show you how to program the IO controller with this RT809F, and with me is having my own tools which I use. This is my TL866CS BIOS copier, which is a very fantastic BIOS copier. You can like flash up to 16 MB of BIOS files. So I would recommend people for this BIOS copy instead of Super Pro if you are into laptop repair, and if you want to flash some kind of advanced chip that is present in photocopier or some other extra devices, then you can go for Super Pro. But especially if you are into laptop repair, I would recommend this Mini Pro. And I have in my home lab this DC power supply. This is Lotus Star DC power supply, and this is a must-have tool. Every engineer must have this tool, because this is used for, you can use this DC power supply in two ways. One is like you can use it as adapters. You are using it to supply the power to the motherboard, and we can also use it to check sorting. So in case of sorting, what it will happen is the volt will go down to 0 and you can increase the current. And we already have one class on DC power supply. And after finishing all this theory class explaining of IO controller PCH, I will have a separate class on current profile, and you can measure the current profile with this DC power supply. Analyzing the current profile will give you a complete view of working. That is also another way to diagnose the problems for laptop motherboards. So I'll cover this part once again. And with me is my favorite oscilloscope, VD2052. This is dual channel and it has a function of auto. So this is also very important, and after finishing my IO controller class and PCH class, I'll show you how to see the entire power sequence on oscilloscope, how we can trace the entire power sequence on an oscilloscope. And without using this oscilloscope, we cannot solve the complex problem, because we must analyze the various signals over here. By multimeter, the multimeter actually shows you the average values. This multimeter, so it gives the average values like 3.3 volt. It will give an average value 3.3 volt. But we must see the curve nature, whether the sine wave is coming or not, or if there is some fluctuation in this. So oscilloscope is an important tool to diagnose the complex problem, and we can trace the entire power sequence on an oscilloscope. So after some classes, I'll have this class also with me. So let us just go to finish our today's class, and in today's class I'll show you how to use this RT809F BIOS copier to program the IO controller. But before that, we must revise our theory once again. So let's go back to the data sheet. The data sheet of KB9012QF. And this data sheet I am referring you to guide the IO controller class. And you can open the page number 25. I have already given you this data sheet. You can open the page number 25, and same as in previous class I have spoken that if you ground this 42 number pin, you see TP underscore PLL underscore lock. This is 42 number pin, and we can open this schematic of 3521. I have with me is the laptop 3521. Okay, this is my 3521, and let's go to page number 1 to see the block diagram of this schematic. And let's go to the page number 2 to locate our IO controller. Yes, and in page number 39 we have our IO controller. So let's see our IO controller over here. Mm, 39. Here in this block diagram we can see there are two kind of BIOS chip, and both of the BIOS chip are connected to the PCH, whereas we do not find any BIOS chip connected to the ENE, because this 9012 has an embedded IO controller, and inside this is 128 KB BIOS chip, 128 KB flash that is present inside this ENE 9012, and we have two BIOS chip. One is for the ME BIOS. I'll discuss what is ME. ME stands for management engine, and we have 2 MB for the system BIOS, that is kind of EFI BIOS. So I'll discuss in the next class what are the differences between ME and EFI BIOS. So let's go back to our page number 39. To find the IO controller. Yes. So this is my IO controller. KB9012QFA3. Okay, and we go again to our 9012QFA4 data sheet. So the first important thing to notice is pin number 42. You can see it's written, this trap is used for E-flash and EDI operation. And if we keep this pin at low means ground, then it will be in test mode. That is, if we ground the pin number 42 of this IO controller, then this IO controller will imagine that I am in a test mode, and this is our requirement. We must put this IO controller in test mode because we are not removing this IO controller from the motherboard, right? We're not removing the IO controller. This is kind of ISP, in-circuit programming. This is ISP programmer, that is stands for in-circuit programmer. So what we will do is we'll supply the three things as discussed in the very first class. In my next class, I've spoken that any integrated chip requires three things: supply, reset, and clock. And in my IO class, I've already said for this IO controller it requires supply. Supply is 3.3 volts. Reset is EC reset, and clock. And since there is no crystal present, it is having an embedded crystal. So supply, reset, clock is already there, right? And if we ground the pin 42, then it will be in the test mode. Okay, so this is a very important pin. We have to ground this 42 number pin. So notice this is point number 1. Okay, this is point number 1. And then we have this table, pin number 59. This is EDI underscore CS. What is EDI? Embedded debug interface. What we are doing is the flash is inside this IO controller and we are trying to program that flash inside this IO controller. So we can access the flash inside this IO controller via these 4 pins. One is 59 number, which stands for EDI underscore CS. And you can see what does it do? It transfers signal from terminal into KBC, right? Terminal into KBC, and here our terminal is our computer and the KBC is here. So EDI underscore CS. CS means chip select. And pin number 60. This stands for EDI underscore clock. And pin number 61. It stands for EDI underscore DIN. And EDI underscore DO, and this is our block diagram. Let's go back to the schematic to understand it more. Yes, and you just go to page number 13. You see over here, this is a BIOS chip, and in the BIOS chip you can see the most important, there are 4 pins. One is chip select, serial output, serial clock, serial input, and one ground. So you can imagine this chip inside it. Let us imagine this chip to be present inside it. So to access this chip, we have to connect these 4 pins: chip select, serial output, serial clock, and serial input, and ground. So here in the data sheet you can see, in the data sheet these are the 4 pins. Chip select, this is 59 number pin, and clock, this is 60 number pin. This is serial input, 61 number pin, and this is serial output, 62 number pin. And the 42 number pin is required to enter the IO controller in the test mode. So why these 4 pins are important? You can see here again in schematic, any SPI chip will have these 4 pins, important pins. One is CS, chip select. So we can see over here we are finding chip select, and we again go over here, this is serial output. You can find here serial output here, and serial clock, and serial input. You can see here serial clock and serial input. So these are the 4 pins. Now what we have to do is, here you can see this RT809F copier. It comes with CDs, so we can install the softwares, and I have already installed the software of RT809F, and this is my RT809F copier. Let us open it. Yes, and you can see if I type 9012, you can see if I type 9012, it will show you KB9012QFA3, and this is the most important thing. This programmer has a facility to diagnose this chip, whereas this same programmer TL866CS, it doesn't have such function. So that's why we are using this RT809F to flash the embedded flash. Alright, so but before this we have to connect these 4 pins. We have to connect these 4 pins of IO controller with this ISP module, right? We have to connect these 4 pins with this ISP module. So let us understand this ISP module first. You can see over here there are 4 and 8 pins. You can see 1, 2, 3, 4, 5, 6, 7, 8. Why 8 pins? Because SPI requires, you can see here, SPI requires 8 pins. So here are 8 pins, 1, 2, 3, 4, 5, 6, 7, 8. And these 8 pins are connected over here. You can see this pin number 1 and 1 is connected, right? This pin number 2 and 2 is connected. Alright, you can see pin number 3 and 3 is connected. I have put my buzzer in the continuity mode, and you see pin number 4, wait, 1, 2, 3, 4. Pin number 4 is connected. Here as pin number 5, you can see pin number 5. So like this, 1, 2, 3, 4, 5, 6, 7, 8. And here is 1, 2, 3, 4, 5, 6, 7, 8. So these are all 8 pins connected with the first 4 pins here and the next 4 pins here. Now what we have to do is, you can see the pin number 1 in any SPI chip is chip select. Pin number 1, chip select. And here in the data sheet we have chip select. This is pin number 59. And we can see in the schematic, let us go back to the data sheet of Dell 3521, and our schematic I was on page number, I think, 40. Let's go back to the page number 40. Yes. And what are the 4 pins? Pin number 59. Let's see what is pin number 59. Pin number 59 is, you see here, is written KSI4. Let us search KSI4. And this KSI4 is connected to the 27 pin of keyboard connector. As we already seen over here, I'll just turn the motherboard, and you can see this is our keyboard connector. This is our keyboard connector. So the pin number 59 of IO controller is connected with pin number 59 of IO controller is connected with pin number 27 of keyboard connector. So we have connected the pin number 59 of IO controller. You see, we have connected the pin number 59 of IO controller. That is, we are not connected. The pin number 59 of IO controller is connected to the 27 of keyboard connector. So, and what is the pin number 59? This is chip select. And where is chip select? Where is chip select? We'll go back to the page number 13. chip select is at pin number 1. So that means we are connecting the pin 59 of IO controller. Pin 59 of IO controller is KCI4, which is KSI4, which is KSI4 is present at pin number 27. So we are connecting the pin number 27 of keyboard connector with pin number 1 here with 1. So what we have to do is we have to connect this pin number 1 of this ISP module, that is chip select with pin number 27 of keyboard connector. Why 27 of keyboard connector? Because 27 is KSI4 and KSI4 is going to pin number 59, and we can see in the data sheet pin number 59 stands for CS, chip select, and CS is pin number 1 of SPI BIOS. So pin number 1 is going to the pin number 27 of keyboard connector. Alright, so what we have done is we have connected this pin number 1 with pin number 27. Alright, similarly we go back to pin number 60, and pin number 60 stands for KSI5. We can see over here once again pin number 60. You see pin number 60 KSI5. Search KSI5. What is KSI? KSI, keyboard scan in. KSO means keyboard scan out. Already explained. I've already explained this in my IO class. KSI5. So KSI5 is pin number 25. So we are connecting the pin number 25. This KSI5 is connected to the pin number 25 of keyboard connector. And what signal is there? EDI underscore clock. And let us see where is EDI underscore clock. We go back over here, page number 13. Any SPI chip, you'll find this in any SPI chip. This is same for any SPI chip. EDI clock. You see, where is clock? Clock is pin number 6. So what is our pin number 6? 1, 2, 3, 4, 5, 6, and 6 is 6. So this 6 will give beep with 1, 2, 3, 4, 5, 6. Right? So we'll connect this pin 6 pin number with KSI5. Alright? With KSI5. KSI5 is connected to the pin number 60 of IO controller, whereas this KSI5 is connected to pin number 25 of this keyboard connector. So we have to connect this 25 pin number of keyboard connector with 6 number. That is, why 6 number? Because this one is EDI underscore clock, and we have already seen this is the clock is at the 6 number pin. Alright, so we'll connect the 6 number pin with this one. So these two are now connected. Now we have to connect the MOSI, that is serial input. You can see this serial input. Serial input is present at pin number 5. So we have to connect 1, 2, 3, 4, 5. 5 is 1, 2, 3, 4, 5. You can see 5 will give beep. 5 will give beep beep. Yes. So this is our pin number 5, and we have to connect this pin number 5 with, you can see again in data sheet, this is KSI6, and we'll find where is KSI6. KSI6 is pin number 28. So we have to connect the pin number 28 to serial input, that is pin number 5. So we have to connect the 5 number pin with 28. Alright, so we have covered the 3. Similarly, this is serial out, and serial out is at pin number 62, which is connected at KSI7 of keyboard connector, and we can see in the keyboard connector KSI7 is connected at pin number 29, and we can see again in SPI clock the serial output, right? So serial output you can see is at KSI7, right? and serial output is over here. Serial output is pin number 2. 1, 2. You can see 2. It will give beep. Yes. So we have to connect this pin number 2 with pin number 2 with this one, with KSI7. And where is KSI7? KSI7 is pin number 29. So this wire 2 will be connected to the pin number 29 of this keyboard connector. So now all the 4 wires are connected, but we have to ground the pin number 42 of IO controller, as this is the first step, grounding pin number 42. And let us see where is this pin number 42 in this IO controller. We go back to our IO controller page 39, and we see over here pin number 42. This is pin number 42, which is connected to KSO3. Let us see where is KSO3. And KSO3 is pin number 16. That means we have to ground this pin number 16. We have to ground this pin number 16. And you see, we have just grounded the pin number 16 of this keyboard connector. I've connected this pin number 16 at the 16 of this keyboard connector with ground. So we have grounded it, alright? And we have to also ground. You can see this is grounded. So now all the configuration has been done. You see, all these 4 pins have been connected, and this is also grounded. Now we can use this. We can use this program, and I've already used this DC power supply as an adapter to supply power to this board. You can see I've supplied power to this board with this DC power supply. And what we have to do, we have typed 9012 and just will press OK, and you see it has done OK. Now the next step is to read the file inside it. So we'll press read, and it is showing a read error auto frequency. That is, this programmer is basically used for programming the LCDs, but we are using it to program the motherboard IO controller. So a little frequency matching has to be done, but this is not needed, and you can see it has already read. And now we can save this file. So we save it Dell IO folder with the name of Dell 3521 EC BIOS embedded, and you can see we already saved it. And this is the folder, and you see this is 128 KB, 128 KB, and you can see in the data sheet the embedded flash present inside this IO controller is 128 KB. So we can use this RT809F to read, write the embedded flash inside this IO controller. But before using this RT809F, we have to configure our board, and configuring our board requires these 4 pins and this 1 pin. That is 5 connections from here to the board. 5 connections, 4 for reading this embedded flash and 1 for entering this IO controller into test mode. And you see I'm supplying the power with the DC supply to the board. I'm not pressed the power button. I'm not pressed yet the power button. By this we are supplying the supply, reset and clock. You see over here 39. We go back to page number 40. Here all these supply is given, EC reset. You can see how to operate this IO controller. 3 things: supply, reset and clock. Supply is already provided 3.3 volt. Regulator will supply the 3.3 supply over here, and reset you can see EC reset, which is also coming from the 3VLW. So reset is also there, supply is also there, clock is there. We have grounded pin number 42. That means the IO controller will now understand that we are in test mode, so it will not generate any other signal, and it will be read by this RT809F. Now in my next class I'm going to cover the entire explanation of this data sheet. I'll cover the entire explanation of this data sheet, and after this I'll discuss about the communication of this IO controller with PCH and the entire PCH, and we'll also trace the power sequence with oscilloscope and the practicalities like how to do BGA, how to clean board, how to use this very good iron eye solder to clean boards, right? So these are the some of the important tools which every laptop engineer should have. And in my next class I'm going to cover the IO controller. So revise this class, and if you have any problems we can get back in touch. And this chip select would also be provided by the IO controller. So during the powering on, we need to check two things. One is chip select and serial clock. We'll discuss the exact steps while checking the IO controller, whether my indirect controller has initialized or not. Then through oscilloscope we need to use the probe to touch these two pins of this BIOS chip, and we have to check the waveform on the oscilloscope for these two signals, serial clock and chip select. Right? Remember about these two important pins. And the SPI interface is used between IO controller and BIOS chip, and also between PCH and BIOS. As we know, there are two types of BIOS chip implemented on notebook motherboard these days. So we go to the next slide, and the next slide is just the representation of what I have spoken. And the very important thing is to how to trace them using oscilloscope, and what are the important things that we need to understand between this SPI interface. And while we go to the practical analysis of how to check the dead motherboards or no display, what are the exact steps, we'll check these important two signals. So remember about these two important points, serial clock and chip select. These are provided by the IO controller. These are provided by the IO controller, because IO is the master over here. Okay, master over here. So we go to the next slide, and this is flash ROM power design. Well, this is a kind of analysis for them who want to build a notebook motherboard. So I'm not going into this detail, but the thing is, there is one situation like if flash ROM is powered earlier than IT8510. Suppose my this BIOS chip is powered before this IO controller chip, like some moment, some very few moment, like the BIOS chip turns before IO controller, and there is very slight difference, like you see maximum 2.0 millisecond, maximum 2.0 millisecond. This is the okay. So now we see EC and EC PACI function. PACI. What is PACI? PECI. PECI stands for Platform Environment Control Engine, and this is one wire bus interface that provides communication channel between Intel processor and chipset components to external monitoring devices. And this is a conceptual block diagram This is Intel processor, and here we have IO controller. So what it's written is one wire bus interface, that is between Intel processor and IO controller there would be one wire interface for providing the temperature measurement, right? For providing the temperature measurement or temperature measurement, right? And you see this is Intel chipset. Between Intel chipset and IO controller there is SM bus. So SM bus can be used to provide the information. But PACE is implemented between Intel processor and IO controller to provide a communication channel, right? To provide a communication channel. And here you can see you fan controlling. We already know the EC controls fan. EC has fan controller, so it can provide this information to the Intel processor via this PACE. And this is implemented in a recent board, in latest platforms, Intel latest platforms. And here in this board, this I think is implemented. So we go down to page number 40, and we can see here is EC underscore PACE, EC underscore PACE, and this is going to page number 4. So where is that page number 4? And you see this is going to the thermal management section inside processor. All right, inside processor. So this is one wire interface in order to provide communication interface between the thermal management section and the IO controller. So this is all a function implemented in newest kind of Intel platforms. So we move down to our next slide, and this is EC GPT and WDT. What is GPT? GPT means general purpose timer, and WDT means watchdog timer. Basically, inside your IO controller you have one GPT, general purpose timer, and WDT, which is watchdog timer. We just need to theoretically understand it, because there is nothing you can do for a diagnostic purpose, but still we need to understand just for definition purpose what exactly GPT is. And GPT, basically the implementation of GPT and WDT is very important when we are dealing with microcontroller, right? Not here when you are going to repair a notebook motherboard. You obviously don't require to understand this, but if you are into microcontroller designing applications, then you need to understand this general purpose timer and watchdog timer. So the GPT is simply a free run timer. While the timer meets a specific value in counter register, it will generate interrupt. And a watchdog timer is a hardware timing device that triggers a system reset while the system encounters any uncoverable situation. So you can just read it through and you can try to understand, and if somebody wants into details, then they can obviously contact me personally. So we go to the next slide, and our next slide is UART. Also, this UART function is implemented in the IO controller, and UART is asynchronous receiver transmitter. And the function of UART you can see in this figure. The parallel transfer, the data parallel transfer is converted into serial transfer. You can see over here parallel data into serial packets, and this is done through EC, through UART function implemented in IO controller. Alright, we go to the next slide, and this is very important, the Intel ICH PCH real-time clock. I will again go through this section of RTC when I'm going to cover the PCH in my next class. I'll revise it, but why I am referring this module, RTC module over here, is because the EC running condition, the EC turning on conditions, when we are going to discuss during the last In my last slide you can see EC working condition. This EC working condition, this RTC plays a vital role. So I'm going to discuss about the Intel PCH real-time clock. Okay, so now we discuss the Intel ICH PCH real-time clock, and this is a very important topic. What is real-time clock? Real-time clock is basically PCH contains a Motorola MC146818 timer. There is one inside the PCH. There is one Motorola IC MC146818B. Okay, and this is having 256 bytes of RAM, battery-backed RAM inside the PCH. And what is the main use of this RTC section is it keep track of time of day, and second thing is it also maintain the system data when the system is down, storing the system data when the system is down. Okay, so what is RTC? RTC is a Motorola MC1468 IC, that is timer, right, compatible real-time clock timer, and this is having 256 MB of RAM. And what is the function of that RTC is, first it maintains the time, and second it maintains the system data. But what the important things to notice over here is chipset using ICH PCH uses a crystal circuit. As we all know in PCH. You can see here, we go to the page number 1 and we see the ICH first. This is ICH. We go to page number 18. Okay, and we move to page number 18 and we have to find here, not here. We go down and see the RTC section. Yes, this is RTC, and you see ICH underscore RTCX1, ICH underscore RTCX2, and this is connected via a crystal, and this is resistor, this is capacitor. So what we are discussing is chipset using ICH PCS uses a crystal circuit to generate a low swing 32 kilohertz input sine wave, right? The input is sine wave, so when you use the probe of oscilloscope to see the waveform over here, then you will find a low sine wave, low swing sine wave, low amplitude sine wave, right? But when you measure the value over here, when you use the probe of oscilloscope to measure the value over here, you will get a high amplitude signal. How does it happen? And we have to understand this phenomena in order to understand whether my RTC section is working or not. If you see the waveform over here and over here, there would be little difference. If there is no difference, then your RTC section is not working. Alright, your RTC section is not working, and this is one solid proof, one solid way to confirm whether my RTC section is working or not, right? So we just go inside the theory, and I've already told you the conclusion. The conclusion is you use the probe to see the waveform over here, you will find a low swing sine wave, whereas if you use the probe to see the waveform over here, the amplitude will be a little higher, and this should happen with a working RTC section. Alright, so we go over here and we see what happens is this input is amplified and driven back to the crystal circuit via the RTC-X2 signal. So what we are talking is, we are talking this input signal is this input signal is amplified by this RTC section. So this value over here, the waveform over here would have some little more amplitude. Alright, will have some little more amplitude. And the most important thing is sus clock, SUSCLK. In many schematic diagram or when we discuss the PCH or ICH, the power timing of all signals, you will find sus clock. And what is sus clock? Here it's written, internal to ICH PCH, the RTC X1 signal is amplified to drive internal logic as well as generate a free running full swing clock output for system use, and this output pin is called sus clock. And basically here we search sus clock SUSCLK. In some kind of board this is implemented, and some kind of board this is not implemented. ICH_sus clock, we see where it is connected over here, ICH_sus clock, and this is very important pin in order to ascertain whether my RTC section is working or not. So perhaps in motherboard where this sus clock is implemented, this is a sure short way to measure, to diagnose whether my RTC section has turned on or not. That is, here you see there is low swing 32.768 kHz input signal, and there is one output pin called sus clock on ICH. Sus clock is different than RTC-X2. You see over here. Don't get confused. We don't have to get confused. We go back and we go back to over here. RTC section. You see this is RTC-X2, RTC-X1. Here the value of waveform would have little more amplitude than this. And the PCH has also implemented sus clock signal, ICH_sus clock. And what happens at this sus clock? The input, this RTC-X1 signal, input signal is amplified to drive the internal logic of this ICH PCH and also generate a free running full swing clock output. And this free running full swing clock output is called sus clock, and here is sus clock. We can see we measure sus clock, and if we measure the value, the waveform value over here by the probe of oscilloscope, then it will give you this kind of signal with high amplitude, not sine wave, full swing. This is full swing signal. Here the input is sine wave, but the output coming from the sus clock is full swing signal, full swing output 32.76 kHz. Mind it, if we measure the value over here by frequency meter, by not oscilloscope, then here the value would show you 32.768 kHz, and here also the value will be shown as 32.7768 kHz. Over here you see, here also it will give you 32.768. At sus clock also it will give you 32.768. What is the difference is shape of waveform. So I always recommend using oscilloscope rather than frequency meter. Frequency meter has no real use if you have oscilloscope, right? Because the frequency meter would give you same value over here, and also at the sus clock. The value is same, but the waveform shape is different. The waveform shape is different. What I am trying to explain is at such clock pin, there would be full swing 32.768 kilohertz, full swing, no low swing sine wave, like this, full swing. And if it's coming, then your RTC section is 100% turned on and working properly. If this is not the difference, then your RTC section is not working properly, and then you don't have to check anything, because RTC is the first step, and we'll see in the next class what I'm talking always about: first step, second step, third step. This RTC section is the first step. Everything in the notebook motherboard, if you are talking about power consideration, the turning on of the notebook motherboard, everything starts from ICH or PCH and ends at ICH and PCH. RTC, PLT reset, RTC, PLT reset. This is start end of power sequence. Mind it, power sequence only, start of power sequence. PLT, RTC, PLT reset, RTC, PLT reset. Everything starts from ICH or PCH. But we have to have some ways to know how to check whether your RTC section is working or not, and this is the perfect way to check. It. So we go we check in the next slide what we are talking about, this crystal circuit. You see in the next slide, this is ICH 1, 2, 3 RTC external circuit, and this is universal circuit. And if you check any notebook schematic having ICH 1, 2, 3, they would have RTC crystal circuit like this only. Similarly, if the notebook motherboard is using ICH4, then they would have the RTC external circuit like this, right? Like this. So sometime you need to check these capacitors also. Some dust is over here, so you need to clean these capacitors sometimes when your RTC section is not responding. When your RTC section is not responding, then we have to check these capacitors. This capacitor, basically this is RC circuit. If you talk about electronics, then this is RC circuit, and I won't go into detail what RC circuit means, but this is all about an RC circuit. We go to the next slide, and here this is ICH 5678 RTC external circuit. So in notebook motherboard implementing ICH 5678 RTC circuit, this would have same circuit. This would have same circuit. All right, this would have same. And here in this diagram you can see this is the RTC external circuit for ICH 5678, and this is universal. Any notebook motherboard having ICH 5678 will implement the RTC external circuit like this. Okay, and we go to the next slide and we find ICH 9 and 10 RTC external implementation. What we are talking about external implementation is this point. We are talking about, we go to the RTC section, and what we are talking of is this one. We are talking about this point, RTC X1, RTC X2, these things, capacitors, resistors. We are talking about these things. This RTC VCC is the supply. The RTC VCC is the supply for this RTC section. And we go to the slide. This is same for the PCH. This is the external crystal circuit for the RTC section. And for platforms not supporting deep S4 S5 will be connected to this. I'll discuss while during the PCH class, because right now to explain this would require some more information. So we'll start this with the PCH. Right now my main concern was to tell about this thing: low swing, full swing and sus clock. We go to the next slide and we go, this is the final slide of our class, and till now we have read and studied all information about IO controllers, the embedded controller present inside the IO controller. We have discussed each functionality of the IO controller, but the crux of all this discussion, all this theory that we have discussed, is to develop a EC working conditions. What are the EC working conditions? And as I always say, we go to the EC of the circuit, and the EC is in page number 31, and here as a basic thumb rule, as I've always said, is any microcontroller requires supply, reset and clock. So these three things is mandatory, and here we have noted plus 3V PCU is EC standby voltage, reset is EC reset. We go to page number 40. Plus 3VP, this is 3.3 volt underscore EC, that is a standby voltage coming or not, then EC reset is coming or not, this is EC reset, WRST, this is coming or not, then clock is coming or not. Three things coming. Then what we need to check? We need to check AC in, AD in, AC in, AD in, AC in, AD in, whether this AC in signal is coming or not, AD in signal is coming or not, right? If there is no adapter, of course this signal won't come, the value would change, but there must be some values over here, and we have to measure then then the waveform over here, this section, chip select and serial clock, whether my EC and flash communication is taking place or not. If my EC, if supply, reset, clock and AD in AC is okay, and the BIOS and EC communication is okay, then my IO controller would generate S5 underscore on. S5 underscore on. This signal would be generated. If this communication is not proper, if IO and BIOS communication is not proper, then also this won't generate. If these two signal AC in AD in is not there, then if your adapter is connected and these two signals are not there, then also S5 underscore on will not be there, and also the very basic supply, reset and clock. So these are the important EC working condition. But we have to see one more thing, and one more thing is, this is one more thing in board where deep sleep mode is implemented. Then what happened is, if my RTC section of the PCH is okay, then PCH will issue sus warn to EC, and EC will issue sus ACK, and PCH will again issue SLP underscore sus, and then EC will issue S5 underscore on. And here we can see the deep sleep mode. Deep sleep mode we have already covered in one of our classes. and I also covered this part while discussing the PCH, but just I would like to show you over here. Yes, this is deep sleep. Here you can see the PCH. Inside PCH there is deep sleep well which is powered by plus ECVCC. So the PCH will then issue sus1, EC will acknowledge it with sus underscore ACK, then SLP underscore sus is issued, and then your EC will generate always on, and when you press power button the RSM reset is generated. So there's a difference between board implementing DPS5. In those kind of board we have to check these signals sus1, sus underscore ACK, SLP underscore sus. Okay, if these three signals are also not coming on, then your IO controller won't generate S5 underscore on. This is the case where the notebook motherboard has implemented DPS5, and we'll use this concept in our next class. So the crux of all this discussion till now is to develop EC working condition. And what is EC working condition? EC working condition is EC standby voltage, that is supply, reset, clock, and then AC in, AD in, then and the BIOS and EC communication, and we can discuss about the BIOS and we can see the BIOS and EC communication by using oscilloscope probe to touch these two pins and to see the waveforms. And where the notebook motherboard has implemented DPS5 function, we have to also see sus1, sus ACK, and SLP underscore sus. And about these three things we'll also discuss in our very next class. So I think you must have got a very fair idea of how to check the IO controller. Till now we have covered the 3.35 volt regulator IC, battery charger IC, and now IO controller, and in the next class we'll cover in complete details about the PCH and the various power sequence and timing. Time is very important function which is implemented on our notebook motherboard. So thank you, and we'll discuss. If you have any doubts, you can always contact me on my email ID.
Good evening everybody, and welcome to the class number 14th. In this class I'm going to describe everything about ICH, PCH and GMCH. And in the previous class we had already finished the working of IO controller, and we have developed the concept of EC working conditions. So in this class what we're going to develop is the correct sequence of any kind of board. I mean the board which is having south bridge and north bridge, and the board which is having just PCH. We're going to develop the powering on sequence for all kind of board, and in a very simple manner. And before going through this class, I request everybody to revise my previous class, because you already know that everything is correlated in this course, and this class is very important, and I request everybody to listen it very properly. So I just go briefly mentioning some points, as mentioned some previous points, as we're already referring two kind of a schematic diagram in this course. One is the Lenovo Y570 and DV2000. So we just go to see these schematics and previous presentation ones for just 5 minutes, and we'll come back with this class. Right? So I'll go and see our previous slide presentation, right? So yes, we already covered these parts: the V in DC bat out generation, the 3 5-volt regulators, the IO controller working, and in very detail we had covered this part, right? So yes, now this is very important. When we press power button, what happens is this NBS on signal goes to the IO controller, and the IO controller immediately releases two signals: RSM reset and SIO power button, right? RSM reset and SIO power button. After the PCH receives these two signals, RSM reset and power button, it releases SLPS4 and SLPS3 signal to the IO controller, right? And what these signals do, we'll see later on. These will open up the suspend voltages we have already discussed. Now after this PCH gets RSM reset and SIO power button, it generates SLPS4 and SLPS3 signal. What happens? Sometime, I mean to tell that sometime what happens is, when you press power button, this PCH is unresponsive, right? That is, there is no SLPS4 SLPS3 signal coming up, right? So what happens? So what can be the problem in that case? We had already covered this part in our previous class, that the very first step of any notebook motherboard powering on starts with RTC section, right? It starts with RTC section. So this is RTC section, and we had already discussed how to check the RTC section in the previous class through oscilloscope, right? Through oscilloscope we had discussed how to check this RTC section. And in the next class, in the next slide, we go to the next slide and we see this four signals. There seems to be non-important, there seems to be unimportant, and it's very easy that people neglect these four signals. But mind it, if these four signals go below than 2.5 volt, then this PCH will become unresponsive, and there would be no signals of SLPS4 and SLPS3 out from this PCH. This is the only case that can happen. What I'm considering the situation? I'm considering the situation that IO controller is releasing RSM reset and power button. After pressing the power button, it is releasing these two signals, RSM reset and SIO power button, but SLPS4 and SLPS3 is not coming. Then what can be the problem? The problem can be your RTC section. So you have to first check whether your RTC section is working or not. And in this class we are going to establish a correct diagnostic sequence, right? A correct power on sequence. In this class we are going to develop a step-by-step procedure of power on sequence, whereby you cannot miss even a small thing, because sometime while repairing we just check major signals, and sometimes we neglect the small things, and that small thing can be a problem. And this was one of the case that I have encountered, we have encountered in our lab, that these capacitors were shorted. This capacitor were shorted. So in this case, if this capacitor is shorted, your RTC section won't work, and if your RTC section don't work, then your PCH obviously can't work, and hence it will not release these two signals, and hence your motherboard won't turn on, right? Now after we go from here, you see RTC section compromises all this, that is, generation of SLPS4 and S3 requires these signals to be present, right? These signals to be present. And after that, after the IO control receive S4, S3, it will generate the sus on, and then all the suspend voltage would be formed on the motherboard. But a very crucial question is that how do we know the exact sequence of this power supply? By seeing a notebook motherboard, can you tell what can be the exact power sequence? Well, everybody would demand a schematic diagram, a circuit diagram, to tell what can be the exact power sequence, but that is half correct. That is obviously half correct, because you know, in all kind of notebook motherboards, like a notebook motherboard like DV2000, where you have a north breeze and a south breeze, mind it, I am just talking about Intel. After finishing the complete chapters, I will take one case study of AMD board. So right now I'm just talking about Intel framework. So what I was talking about is, suppose we don't know these sequences, suppose we don't have a schematic diagram, and can we tell without going through the schematic diagram what can be the exact power sequence? What can be the exact power sequence like? Suppose consider example like DB2000, we have a two kind of breeze, north breeze, south breeze, and consider example having 5010, which is a PCH. Can we tell what can be the major differences in the powering of a DB2000 board and 5010 board? Well, it seems a very good question, and of course you can tell. By seeing notebook motherboard, we can have 98% idea how this notebook motherboard will turn on, will power on, and we are going to develop that strategy and concept. We don't have to always look through schematic diagram to get an idea of power sequence. We have to just go through a schematic diagram to see the specific resistors, capacitors, and the pin numbers, not the sequence. That is what I'm going to tell you, is that we should develop the exact power on sequence, and of course the power on sequence is fixed. Power on sequence is fixed. That is, all boards having ICH9 will have same kind of power sequence, maybe some little bit of changes, but 98% they would have the same power sequence. All kind of board having HM55 PCH will have same power sequence.
but there would be differences in power sequence between HM55 and HM65, HM65 and HM76. So what I'm going to tell you is that we have to develop the concept based on Intel chipset, because what is common among all these boards? Common among all these boards is Intel, right? Intel processor, Intel chipsets. So we have to develop concept based on that processor and chipsets, right? Not on boards. Dell board, Toshiba board, Sony board, HP board, any kind of board. What we have to develop concept is based on processor and chipsets. So in this class, we are going to develop that concept. So I just go back and start with the today's class. What I wanted to tell you is that the power on sequence depends on chipsets, right? Depends on chipsets. ICH9, ICH10, Intel series 5 chipsets. That is HM55, HM57, these are called Intel series 5 chipsets. Intel series 6 chipsets are HM67, HM65. Intel series 7 chipsets are HM76, HM75. And the power on sequence of all HM55 boards are 98% same, right? 98% same. Whether that board would be manufactured by any kind of company, be it Dell, HP, Toshiba, all these boards having HM55 will have 98% of power sequence same, right? So, and we are going to develop the exact power sequence, because if you know little things will make the task very difficult, right? So we're going to develop the exact power sequence in the today's class. So before developing that concept of power sequence, I'll discuss how does the Intel has combined these all components in their boards. So we start with the today's class, right? We start with the today's class. Okay, so now we start with the today's class, right? So yes, Intel chipsets and processor naming. This is a very interesting table, and I request everybody to just print out this slide and fix it wherever you are trying to repair it, right? Because you see, in schematic diagram, suppose in a schematic diagram in processor it's written penrine. Penrine means code to duo processor, right? So if you are confused, sometimes what happens is your processor is faulty or your notebook motherboard won't work if you do not insert the correct processor, right? Correct processor. So what you have to do is you have to just know what kind of processor it is written, because in the schematic diagram the exact processor to be used is written. Penrine. Penrine means core to duo, right? Similarly, you see Arendelle processor, then Sandy Bridge, Ivy Bridge, Haswell, Broadwell, Skylake. These are all the code name. But if you type this Arendelle processor in the Google, it will give you all types of Arendelle processor, and you can insert any kind of that Arendelle processor or any kind of that Sandy Bridge processor in that motherboard, right? In that motherboard. So what we are going to focus is that the relationship between the processor and chipset. You know, every type of processor, every different type of processor has a different chipset. So the core to duo, that is Penrine processor, in that kind of board you will have two kind of chipset on the notebook motherboard. One is North Breeze, another is South Breeze. South Breeze would be named as ICH1 to ICH10, that is starting from ICH1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Whereas the North Breeze, if you want to go to see the data sheet of North Breeze, then you have to type something like this: Intel series 1 chipset, Intel series 2 chipset, Intel series 3 chipset, Intel series 4 chipset. That is, from Intel series 1 to 4, all of them are GMCH. graphic media controller hub. And examples of North bridges are AC82 GM45 and AC82 GL40. After Intel series 4 chipsets, the Intel combined some part of North bridge into South bridge and some part of North bridge into processor, and Intel now reduced the number of chipsets from 2 to 1. So Intel series 5 chipsets stands for PCH, platform controller hub, and Intel series 5 chipset is also called IBEX PIC. So in a schematic diagram, if you see in PCH it's written IBEX PIC, that means it is Intel series 5 chipset, right? Similarly, Intel series 6 chipset is called Cougar Point, C-O-U-G-A-R, Cougar Point, and the processor supported is Sandy Bridge. Similarly, Intel series 7 chipset is called Panther Point and the processor supported is Ivy Bridge. Why I'm talking about this table is very important, because when you go to a schematic diagram or when you find any kind of board, then it will be very easy to see the power sequence, because all the power sequence is mentioned in the data sheet of Intel, right? If you find in the schematics diagram IBEX PIC, what you have to do is you have to just go into the data sheet of Intel series 5 chipset, and there you can find the exact power sequence. So wherever you get Cougar Point, you will get Intel series 6 chipset. We just see what I'm just talking. Just let's see over here our schematic diagram that we are referring in this class is this one. Yes, see. Yes, you see in this data, see what is written? Sandy Bridge, Cougar Point. Sandy Bridge, Cougar Point means, you see, Cougar Point means Intel series 6 chipset. So I don't know what is the chip number, but I can 100% say the chip, the PCH would be HM65 or HM67, right? Just saying this Cougar Point, because what is Cougar Point? Cougar Point is Intel series 6 chipset. And what are the types of Intel series 6 chipset? It is something like HM67, HM65, QM65, QM67, like this. So without seeing the chip number, I can just tell what can be the PCH, what can be the numbering on PCH, and I can also tell the exact power sequence of this board. 98% power sequence I can just tell just by seeing the PCH, and that is what I want to develop among you, not to look every time a schematic diagram. Just get a 98% idea by seeing the notebook motherboard. You can get a 98% idea how the powers are flowing, right? If you get a 98% idea just by seeing notebook motherboard, then you can repair it very easily, and all that is the exact power sequence. You don't have to just go in the schematic and try to find where is my power sequence. No, you can just tell it by seeing the PCH, by seeing the ICH. You can just tell by seeing this chipset, right? So we just, yes, the second slide. So I request everybody again to print it out and fix it where you are repairing. Intel series 6 chipset, Cougar Point. Intel series 7 chipset is Panther Point. Intel series 8 chipset is Linux Point, and the processor supported is Haswell. This is very important, because when we are going to talk about the core voltages, then we'll talk about Haswell. This chipset has embedded voltage regulator. You won't find VRM, external VRM in the board, no, because the VRM is integrated in Haswell. that is fiber, fully integrated voltage regulator. And if you don't have this idea, they will keep finding the VRM, right? This processor has integrated VRM. That's why it is called fully integrated voltage regulator, fiber, right? Then Intel Series 9 chipset is called Wildcat Point, and the processor support is Broadwell. This is not having fiber, only as well as integrated voltage regulator, right? Integrated voltage regulator. So we move to the next slide. Yes, and before developing the exact power sequence concept, I just go to discuss the basics of Intel architectures, and in this we'll cover the power, clock, sequencing, power states, and the input outputs, and also the RAM and clock working. Before entering the power sequence, we have some basic concepts of Intel architecture. So we go to the next slide, and we're talking about the power, that is Intel architecture. What are the powering requirements for Intel architecture? As you know, in a notebook motherboard or a desktop motherboard, whatever be the Intel architecture, that is we call IA designs. What IA designs stand for is Intel architecture designs, and that can be anything that Intel has made. Maybe it may be the notebook motherboard, desktop motherboard, or mobile phone, anything. So mostly two kind of voltage regulators are used by Intel, that is switching and linear. We already have a fair idea of this kind of regulator because we have already gone through the class of 3.35 volt regulator IC, where we had discussed the switching and the LDO. So the LDO is linear, right? And the switching is that switching regulators. So what we are talking is the Intel architecture requires two kind of voltage regulator. One is switching and linear. And let's talk about switching regulator. We have already discussed the most kind of switching regulator that is used in notebook motherboard is buck regulator. Buck means lower down. We require always a lower voltages from input voltages in notebook motherboard, right? We hardly find a scenario where you require more voltages. Only in case of inverter. Only in case of inverter, where you require a high AC volt, right? You require a high volt. That's why we require an inverter. But mostly in all the power area of notebook motherboard, we require a lesser voltage. So buck regulator, buck switching regulator is used mostly in the Intel architecture. And there is one special requirements for CPU core voltages, because you see in this diagram, as the load current increases, the core voltage has to go down. This is the CPU voltage load line, that is the VRM. The regulator that supplies the core voltages has to adapt this scenario, because CPU core voltage regulator is different than other voltage regulator. How it is different? Difference is that in most of the regulator the output is fixed, right? The output is fixed, whereby in the core voltage regulator it can vary from 1.12 voltages to 1.02 voltage or maybe lower, depends on the processor type used. Because as the load increases, that is, as the graphics intensive work increases more, there can be a decrease in CPU core voltage, right? This is one difference. We'll go to see another difference, and this is the tolerance band, right? This is the tolerance band. We call it DC tolerance of core voltages. So these are the two special things that we will discuss right now about core voltage. Why I am discussing before the power sequence, that because we will use these concepts while discussing the power on sequence. So mind it,
check the minute details that I am talking about right now. What I am talking is the CPU core voltage load line and the tolerance band. These are the two special differences that a CPU VRM has, right? Another difference is you may find in the VRM section VID lines. We'll see in our schematic, right? We'll see in our schematic the core voltages, and that is page number 49. So let's go to the page number 49 and we just zoom it and we can see. Just zoom it more and you can see, we can see this problem of VID. You can see here, you see these pins are known as voltage identification pin, and in desktop motherboard this is called VR hash nomenclature. That is, while searching for the data sheet of desktop VRM, you can find it like VR11, VR11.1, whereas in mobile, in notebook, that is mobile design, that is notebook, this IMVP is used, Intel Mobile Voltage Positioning, and you can see this VID pins in the voltage regulators, but this is IMVP, right? IMVP. So this IMVP is much different than the previous voltage regulators, and here you will find no VID pins. You will find just SVID data and clock, right? SVID data and clock. By this data and clock, it gets the inputs to rectify the core voltages, So this is another difference. So what are the three differences that we have talked about a core voltage regulator? One is load line, second is DC tolerance, and the third is the VRM have VID pins. In the older voltage regulator you will find pins, voltage identification pins, but in notebook designs, the newer kind of voltage regulator, you won't find dedicated VID pins. There is SVID data clock pin, right? Data clock pin. So this thing is missing from the other voltage regulators, right? We go to the next slide, and we'll talk about linear regulators. We already talked about switching voltage regulators, and now we talk about linear regulators. Why linear? What is the use of linear voltage regulators? The question stand is, why do we require linear voltage regulator? Well, when we are using the concept of ACPI, Advanced Configuration Power Interface, then the concept of standby power. You know standby power? Standby power, when you are using SMPS, when you are plugging the AC switch, a standby voltage is already generated. Similarly, in the notebook motherboard, when you plug in the adapter or when you insert the battery, even when you do not press the power button, you already have a 3.3 volt. We already discussed. This is all about the standby power supply. And we see in the 3.3 volt regulator discussion, we already seen there is a generation of 3.3 LDO, right? Generation of 3.3 LDO. This is all about standby power. So that is why we require linear regulators. Now we go to the next slide and we talk about clocking. We already talked about power. Now we talk about clock. So in the Intel architecture platform, basically we'll see about these following frequencies. One is the 14.318 megahertz, and this is the standard clock frequency used by the clocking devices, right? We will see later on where this 14.318 megahertz is used, and we already know 32.768 kilohertz is used by Intel chipset. Then another important frequency is BCLK. This BCLK, what is BCLK? The CPU has pins that connect to the clock chip to to program the output frequency of primary CPU clock, right? That is, the CPU send message to clock generator to give exact frequency, right? Because you have a different kind of CPU. You see over here, core Penarine. Penarine means all type of processor code named as Penarine, but all type of processor can have some different frequencies, right? So when you insert the processor, it will program, the CPU will tell to the clock generator via BCLK to program the base frequency, base clock. We'll discuss it later on. And another important thing in Intel clocking is spread spectrum clocking. Spread spectrum clocking. What is this spread spectrum clocking? The principle of SSC is that the clock chip continually varies its output frequency over a small range centered around base frequency. We'll discuss about this thing while we discuss the clock generator just after 2-3 slides afterwards. So till now what we have discussed? Till now we have discussed about the Intel architecture basic powering, right? And in the power we had discussed about the switching regulators and the linear regulators, and now this is clocking. And in the Intel architecture you will find about 14.318 megahertz, you will find about 32.768 kilohertz, you will talk about BCLK, we will talk about SSC. So I am giving a preview of all these things that we are going to talk later on, right? So we go to the next slide, and in the next slide we will talk about the power on sequencing. Now there are two types of boards that we are going to talk about. One is the desktop board and another is notebook motherboard. So in the desktop board there is ATX, right? We use SMPS. Whereas in the notebook motherboard we use the combined design. So we go to the next slide and we'll talk about this sequencing a little more in depth, right? A little more in depth. Okay, so we talk about the sequencing, and as we have spoken, there are basically two kind of Intel architecture designs that we are talking about. One is the desktop motherboard and another is laptop motherboard. There are some little bit of differences between a desktop motherboard and a laptop motherboard, and what is the major difference is ATX power supply. In a desktop motherboard, in a desktop you have a SMPS, right? And that SMPS, in that we are talking about 4 positive voltages and 2 negative DC outputs, right? You can see in the SMPS 3.3 volt, 5 volt, 12 volt, 5 volt standby, and -5 volt and -12 volts. These are the 6 kind of voltages that we talk in desktop power sequencing. And there is a power sequence for desktop motherboard as well, but we'll talk in a special class about the desktop motherboard, right? We'll talk after completing the notebook motherboard. We'll talk little about desktop motherboard, how it is different than a notebook motherboard. So this is all about the sequencing. A very important thing that we have to note down is the basic sequence of power in an Intel architecture starts with standby rails. That is, first a standby power supply generated, then progresses to chipset and CPU IO voltages. That is, first the standby voltage is generated, next chipset and CPU input output voltage is generated, after that chipset core voltages are generated, and finally CPU core voltages are generated, right? one thing we must note and understand is that everything in the notebook motherboard is we are talking in respect to chipset, PCH. Everything starts from PCH and everything ends at PCH. That is, everything basically starts from PCH and ends at CPU, but the entire power sequence is governed by PCH or ICH that we are talking from very first class. So note down this statement. This is a very important statement, and we can correlate everything that we learn in this class. It's summarized over here. That is, the basic sequence of power in an Intel architecture system starts with standby rails. First, the standby power supply generated, then progresses to chipset and CPU high voltages, then CPU, chipset and CPU input output voltage generated, followed by chipset core voltages, and then finally CPU core voltages, right? And how does this sequence operates? This sequence operates on the phenomena of power good signals, right? It is expected that this sequence is forced by way of power good signals from one state to the next. That is, when one state crosses, it generates a power good, and then the second state begins, right? So this is very important, and voltage regulators are commonly available with this power good type of output signal that becomes active when the regulator output is valid. The final power good indication is from CPU core voltage regulator, and this power good is used as the final signal to the chipset to convey that all power supplies are on and ready. Once the power rails of Intel architecture components are valid, the final power good signal to the chipset let it de-reset the system and CPU reset signal. At this point, CPU will start a defined process to begin executing instruction from system BIOS. That is, the entire power sequence has been summarized in these words. So what is the meaning? The meaning is that first standby power is generated, then chipset and CPU high voltage generated, then chipset core voltage are generated, and then CPU core voltage are generated. And how these sequences go on? These sequences go on by generation of power good from the voltage regulator. Once power good is generated, then the second step progresses, again power good generated, again next step progresses, and when the CPU core voltage regulator generates power good, that is the final point, and the CPU de-assert itself and the CPU starts reading BIOS. This is the entire concept of power sequence in these few words, right? So we'll analyze this entire that is, you can say this is the concluding remarks. This is actually the concluding remarks, but now we are going to decipher this conclusion, how we conclude to this point. We're going to understand about that, right? So we go to the next slide, and these are the power states. We have already discussed about the power states in the previous class. That is S3, S4 and G3 mechanical off. These are mostly the important power sequences. So, and now we'll talk about the RAM concepts. I'm talking about the concepts before, so that when we are talking about the circuit diagram or schematic, we're not getting confused, right? We're not getting confused. So these are the basic concepts that I will talk before I enter into the explanation of the power sequence in this class, right? So, well, I've already discussed this statement of power sequencing, but I would like to revise this through a diagram which I had edited in this presentation, because this concept is very important. the entire concept of power sequence is described in this little diagram, so we'll just discuss this thing. Any notebook or any Intel architectures starts first with standby rails. That is, first the standby power supply is generated. And what is standby power supply in case of notebook motherboard? It is 3.3 volt. 3.3 volt is the standby power supply generated on the notebook motherboard, and we'll discuss this concept. This is the basic concept of any power sequence of any notebook motherboard or any Intel architecture. Intel architecture stands for desktop motherboard, Intel motherboard, or Intel mobile phones. Any Intel architecture will have this same power sequence. That is, first standby power rails are generated, and then through a power good signal, chipset and CPU input output voltages are generated. Chipset will, when we are going to discuss the individual ICH9 or Intel series 5 chipset, 6 chipset, we'll see all of these signals. This is the crux of power sequence. What is the crux of power sequence? First standby rails are generated, then chipset and CPU input output voltage are generated, then chipset core voltage. I mean to say that any chipset will have two sections. One is input output and another is core and another is standby. So first the chipset standby supply is generated, second the chipset input output is generated, then the chipset core is generated, and after that the CPU core is generated. So these are the four basic sequence, and this four basic sequence can be divided into many steps. It can be divided into 8 steps, 10 steps or 12 steps, but this is the basic power sequence. What is the basic power sequence? First the standby rails are generated. What is standby rails? A standby power for chipset, then chipset input output voltage generated, then chipset core voltage generated, and then CPU core voltage generated. And after the core voltage are generated, a final reset signal is issued to the CPU by PCH or ICH, and then it will start reading from a BIOS. So keep in mind this power sequence for understanding any kind of Intel architecture, right? I have studied almost all type of Intel architecture, and after studying this Intel architecture, I have developed a very basic concept of power sequence. And if you're trying to repair any kind of devices other than notebook, then you will find this diagram to be very useful, right? So we'll go ahead and we'll go to the next slide. Yes, the power states. We had already discussed this power states in the previous class. And what are the common power states? First is G3 mechanical off, right? Then second is S5, then third is S4, then S3, and then S0, right? These are the common power state. We had already discussed these common power states, and you can go through this slide again if you have missed my previous class, right? So I won't go into explaining these things, so we'll just go to the very next slide and the concept of RAM. And I'm discussing the concept of RAM before the power sequence, because we are using some some concepts of RAM while discussing the power sequence. So what is exactly a RAM, and what is the most important thing in a RAM? RAM is a dynamic random access memory. Why dynamic? Dynamic is that in RAM there are many capacitors present, right? So what the capacitor does is the capacitor stores charges, right? The RAM stores data in form of capacitor charge and discharge, right? That is a very basic concept of storing data. How does RAM store data? RAM store data in form of 1001, 1001 like this. And how does they symbolize this 1001? They do it through a capacitor charging, right? But you know, a capacitor, very basic concept is leakage. A capacitor can leak the charge. If you don't recharge the capacitor, it will start leaking. So my data will be corrupted. So in order to prevent the data corruption, what is important is memory refresh. Memory refresh, and that memory refresh is a very basic and inherent in any kind of RAM. That is, memory refresh is the process of periodically reading information from an area of computer memory and immediately rewriting the read information to same area without modification for the purpose of preserving information. That is why always RAM require memory refresh. RAM require memory refresh in order to prevent the data loss, right? In order to prevent the data loss. That is, and why I am discussing this memory refresh is that while you are in S3 state, right? Let's see in the previous slide, S3 state. What is S3 state? Commonly referred to as standby, sleep, or suspend to RAM. That is, RAM remains powered, right? RAM remains powered, and we have to make the RAM powered on, right? We have to make RAM powered on during S3 state. That is, memory refresh is possible in S3 state, right? Why I am discussing this concept right now here is because we are going to correlate these concepts in later on. So in S3 state, we require RAM refresh, right? We require RAM refresh because RAM is powered on. The context is saved in S3 state. You see, RAM remains powered on, but all non-standby power rails are turned off. But during S3 state, there is no clock generator, so you don't have clocks. So how would RAM do it refresh? How would RAM do it refresh? Now this is a very good question. The question is that we call S3 state as a state where the context is saved in RAM. That is, the RAM is powered on and RAM refresh has to be done because the context is saved in RAM. What do you mean by context? Context means when we power on the notebook motherboard from S3 state, it will turn off at the same place from where everything is starting. That is, no data loss in the RAM in S3 state, right? But when RAM is powered on and context is saved in RAM, then memory refresh has to be done because memory refresh is an inherent fundamental of RAM. If there is no memory refresh, then data would be corrupted. But memory refresh is done by clock, you know. We'll see later on. We'll see in the schematic. Memory refresh is done through clock. But we know in S3 state, there is no clock generator. If we take a case of ICH9 where there is an external clock generator, we don't have clocks, right? So how would RAM preserve the data? Yeah, this is a very good question, and I will answer this question later on. We'll use the concept of sus clock. Sus clock, you can see in any schematic diagram, you will find sus clock. And what is sus clock? Sus clock is suspend clock. Suspend clock. And how it is generated? We have already discussed in the previous class. It is generated through the RTC section of PCH, and that's why RTC section is very important, and it is that's why started in the beginning, because it has two things, two fundamentals. One is to give clocks internal to the PCH and also to generate a suspend clock. Suspend clock. We'll see in the schematic diagram what is the use of suspend clock. The second thing is on-die termination. Well, this is a very important concept. Why termination is required in RAM? Why a termination registers are required in RAM? You'll find in notebook motherboard having DDR1 RAM, you'll find termination registers just besides the RAM slot. Whereas in board having DDR2, DDR3, you will find them missing. You will find termination register in some board missing. How is that? And what is the use of termination registers? What exactly is the purpose of termination register? Now listen to my words very carefully, what I am speaking till now, right now. See, in a notebook motherboard, we'll take the case of a schematic diagram. Let's take DB2000 case, and the RAM slot you see in this schematic diagram. In this schematic diagram, you can see in notebook motherboard, this is the data communication between GMCH and RAM is taking at very high frequency, it is taking at a very high frequency. So it is taking as a very high frequency, so we cannot use the concept of lumped circuit. What is lumped circuit? We mean by lumped circuit is that voltages is fixed at each of the point. Well, there is a direct connection between GMCH to the RAM, but we cannot consider voltages to be same between here to here because the data communication is taking place at a very high frequency. So it cannot be considered as a case of lumped circuit. Lumped circuit, lumped circuit is considered where you can consider the voltages between here to here as same, but we cannot consider here the voltages to be same when the data communication is taking place at a very high frequency. There is differences in voltage, right? There is differences in voltage, so we have to consider this as transmission lines, right? Transmission line. As a transmission line, what is transmission line? Transmission line is a very is a situation. You see how electricity comes to our house from a powerhouse. It comes through transmission line. The current flows miles, kilometers before reaching our house. So we can consider this small distance between GMCH and RAM to be a transmission line, not to be a lumped circuit, not to be a small circuit, because the data communication takes place at a very high frequency. So we have to consider as a transmission line. And in transmission line, in order to offset the resistance, we use the termination register. In order to offset the resistance and capacitance in between, we use termination registers, right? We use termination registers. So you can see what is it, because there is a impedance mismatch. Well, I won't go into much detail, but we can also derive this as mathematically, and we had done this derivation mathematically in the class of transmission power while I studied electrical engineering. So that's why I had correlated the concept of termination registers. Why termination registers is required? Termination register is required because the distance between the DDR RAM slot and the GMCH can be considered as a transmission line.